Right. Keyboard was already AI lab, which is since the next slide, introducing our lab. There's energy lab, so we are a lab between 3ME and EMCS faculty. We basically offer some education, machine learning for electrical engineering, where we're looking into the applications of electrical engineering, how we can teach through those to electrical engineers machine learning methods. Next week, we kick off a new course, Machine Learning Workflows for Digital Energy Systems. And then we have a few partners because we are working on the power system. We work closely together with system operators like Stedin, Tenet, or Alliander. But there are differences in the power system. Because Tenet is responsible for operating the transmission system, and Alliander and Stedin in the Netherlands work on the distribution system. And maybe some questions for you at the beginning is anyone else working on the application of power systems? Or you're working on any, like applying graph neural networks or developing graph neural networks or graph-based methods for other engineering disciplines? Yeah, maybe 3, 4. Okay, which ones are those? Just curious. Which applications are you looking into?
I work with flooding.
Flooding, okay.
Transport.
Transport, nice.
Chemical processes.
Chemical processes, great. Okay. We work on the power systems, and also here we have a list of collaborators and people who work on the power system together. I think Jochen is missing on the slide, but we have now expanding our group recently on this topic of applying graph neural networks for power systems, and our earlier research through Elvin and some collaborators from industry, and Benjamin Habib, also group member. And also today I'm giving you a glimpse into the research which we have done so far. And then Ola will also present some of his research later after my talk. So let's start introducing power systems, because I think not everyone may be familiar with it. So maybe one first information is that the electrical system in the European Union is completely connected, right? So your plug in the wall is connected with another plug in South Italy. So there's no disconnection. And it's really the largest system we have, human built in the world. And we typically have this hierarchical flow of power from a generation station, this may be wind park or conventional generation, nuclear power, or others, towards the end customer, which may be then your household, or which may be industry connected to the medium voltage system. Now, this system has different structures. If you think from a graph perspective, mimicking the interconnection of the system. Distribution systems, for example, are more meshed than transmission system. So that's, let's say, the power system. You have in between always transformers, which change the voltage levels from one to the other. Here we are in 230 kV, and here 100 to 240 volts. So very different order of magnitudes. But still, the system is interconnected. So in a lot of the research, we look into this kind of power systems. So this is high voltage system, right? Which you maybe see when you go on the highway and you drive to Amsterdam or so. You see those big power systems. But then we have also distribution systems. And distribution systems are slightly different. So they interconnect, let's say, part of a city, right? We have basically low voltage system, which is within one neighborhood. We have medium voltage system, so that's on the order of cities, where also industry is connected to. And then we have high voltage system, which connects cities in between, and also countries between, and so on. So these are the 3 voltage levels, and here we are looking into the medium one, so medium voltage system, where you can see we have transformators here in blue, and then we have connections to the high voltage buses, for example, here and here. So you can think about different hierarchies of this graph, right? This is the medium one, and in each of those points, or in some of those points, are also underneath low voltage systems. So medium voltage system bus, medium voltage, low voltage buses. So this is where this interconnected to a low voltage system, right? And then this one is a connection to the higher voltage system. So here we look into medium voltage system, and this is the typical or one example architecture of this graph, or topology of this graph. Now, in this medium voltage system, we may have different measurements. We have power flow measurements here, where we can measure how much power goes through this line. We have voltage measurements, right? So these are other state variables which we have in the system, which we can also not observe everywhere, or we cannot measure them everywhere. But in certain locations, the system operator has placed measurements, and there we have access to those. Yeah, and then all gray is basically interconnection between these buses. Yeah, so now, of course, there are a couple of problems within this medium voltage system, because we cannot measure all of this information all the time. But the system operators need to ensure that there is no overload on any of those lines at any moment, right? So the power flow goes either from here to there. Firstly, in which direction does it go? How high is the power flow? Do we have an overload or not? We can also not much control there actually in real time. So having real-time estimations on this is very important. And of course, we know the physics, we know how this network works, we know Kirchhoff's law, so we have a lot of knowledge at the same time. But we have also a lot of data, right? And that's also where these two worlds now merge in our research, right? To extract information from this data using the power flow equations and the Kirchhoff's law to answer questions which system operators have. Like, what is the state of the system? How should we operate it? What can we do to avoid overload? And ultimately to integrate more renewables in the system. Because what's now changing is in each of these buses, right? In each of these, there's a neighborhood underneath, which was not designed for having electric vehicles, for having photovoltaic on the system. So it was designed in a different period of time, decades ago, and was designed for very static power flows. But now the situation changes, right? So we need to figure out, is the system accurate? Where do we need to build new lines? Lots of different questions. And a lot of these questions are typically answered with power system analysis tools. So the power system operator may have a replica, a model of this system, right? Because they know to a certain extent how the system is interconnected, what is the parameters of these lines, what are the physical parameters, and you can put this in a power system analysis tool or model, and you can answer certain questions like, where should I connect my line to minimize the overall loading in the system, or something like that. The challenge is that quite often these power system analysis tools do not scale very well to the number of buses. So if you think about the number of buses, so here, I don't know, this may be in the order of 100 or something like that. If we have a system which is even larger, then the computational time to analyze the power system and making these decisions scales poorly with the number of buses. So the more buses we require more computational time to make those decisions. Right, and here you see this in O notation. So very often we are here in this order to the power of 2 and 3. It depends, of course, what kind of analysis we are performing. Right, and each model analysis may have different computational complexities, but we are not really here in this order, but most of the time in exponential or in higher orders. So, for example, reliability assessment is another example where you are interested to assess how reliable the system is if a failure occurs in the system or so. So this is one challenge which we have in power system analysis, but also applying AI to address these issues is not very straightforward. Because there are still existing barriers with AI. So one is, for example, that we have struggles to generalize to out-of-distribution data. So that's maybe now a bit general information. But if you think about the energy scenarios, right? So now let's think back to the situation I presented to you. The system is always changing. We have more electric vehicles in the system and so on and so forth. So we know that the future energy scenarios will different in the future different to the past, which means that we need to make sure if we learn with machine learning and making those decisions that we are aware that this happens, and particularly there we have issues to generalize to out-of-distribution data if we train on historical data only. Then second one is we have very large system, which also means we have large training data. And power systems are extremely large systems, so that's the second challenge. And the third one is that the power system is safety critical, because your energy supply and the security of those depend highly on how we operate the system. So if we rely on any AI method, we need to either have explanations or formal guarantees or such. So this is also then a third challenge. So very often to address these challenges are presented early with the power system analysis. There is an approach to use machine learning for it, which is to basically learn surrogate models, right? Where you can train it either on a smaller system or on different data or on labels you create already on the power system analysis tool. And then you learn a surrogate model and you apply this. And then maybe you can go to larger systems, or you can do it in faster manner, right? So instead of doing the power system analysis in the order of minutes, maybe you can then solve the problem in a second or subsequent level because you are using a trained surrogate model. But actually, we are translating the problem from one to another, because what typically it leads to is that we require quite a lot of training samples if we grow in the number of buses. And power system analysis, to do this for small systems is no problem, but it's a challenge if you go to larger systems. If we are training surrogate models for power system, there is no use case for doing this for smaller systems. So the ultimate use case would be also to do it for large system, but then we have a similar scaling behavior because you require more and more training samples the larger the system becomes, typically, right? And this leads me to the challenge in machine learning, which is the curse of dimensionality, which probably some of you are very familiar with. So the curse of dimensionality is basically you have in, let's say, 1 dimensions, you have a certain number of samples, you have maybe 3 different classes, and we can all agree that in these 3 regions here, we would say we have enough information to learn a classifier on this data, right? Because we have here, what is it, 4, 8, 10, 11 samples over 3 regions, so sufficiently covered. But if you go to 2 dimensions, you see already the same number of samples does not cover anymore all regions. So 3 regions are empty. So we do not have any information if there is a circle or a triangle or a star in any of those 3 regions. So if we learn a classifier, yeah, we don't know if there's what will be there. And then if you go to larger dimensions, this becomes more challenging, right? So this means more 3D regions will be empty, and you go to larger dimensions and this becomes then hopeless. That's the curse of dimensionality. So it's basically the same story I made. The larger you go in the dimensions, the more samples you would need exponentially, or you have this combinatorial explosion. So now, what is the possible solution? Or one approach which we are looking into also in our research is to learn without labels and induce bias through the physics. And there are different kind of like categories of learning which are currently being used and investigated for this use case. Self-supervised learning, physics-informed machine learning, or weakly supervised learning. And the goal is to basically use, and this is also where graph neural networks come in, through the neighborhoods, we have more information. So one snapshot contains multiple of those neighborhoods, and that possibly can address this issue which we have with the curse of dimensionality. That's the hypothesis. We have not yet really confirmed this hypothesis sophisticatedly yet, but that's basically the vision of this plan. So that's the high-level vision or introductory part of this talk. And now the second part will be on one example we have been carrying out through Benjamin Habib and in the collaboration with Elvin, which is the problem I introduced slightly already, the problem of distribution system state estimation. So in this challenge, or in this problem, we assume we have a certain number of measurements Z with a noise vector. We have M measurements, and we have a system state we are going to estimate. That's the objective. And we have 2n of those state variables. So the objective is to go from the measurement Z to the state X. And now the challenge is that M is significantly smaller than N, so which we call is partial observable. We have very little measurements. Remember earlier this figure I showed you with the distribution system? You may have spotted there are just a few red dots, right? Or a few dots where there are measurements. So that's the challenge. And the goal of state estimation is, as mentioned, is to go from Z to X. Yeah, here I show it again. So you can see again voltage measurements and power flow measurements. This is basically the input of the function f of z, right? And all on those orange dots, we have state variables, which we are going to estimate 2 of them. So each bus we have voltages and phase angles. Two values, and the red points are where we have measurements, and the green marked lines. So what do we else have available? We have, I mentioned earlier, Kirchhoff's law. We know the power flow. We know how it works. We know the physics. So from there, we can derive the model of the power flow. So this is basically a physical model which maps basically X to Z. Yeah, I don't go through them, but this is voltages and phase angles. These are the 2 I mentioned already, which also define our state vector X. And then that is basically this, what we call measurement function, h of x, which is the set of these equations, plus the noise vector epsilon. And here's another illustration. So you have buses and lines in green and red. These are your features, for example, which we have either on buses. So I mentioned earlier, we have voltages and phase angles, but we have also active and reactive power injection at each bus. And then we have here the Y-bus matrix. We have I, P, and Q, P. And Q is basically active and reactive power flow over this line. And I is the current. Yeah, so this is just a small illustration of these kind of equations and the variables which we have. Okay. Now, the distribution state estimation problem has been studied for many decades. And there is actually one state-of-the-art method, or it's one of the example methods. There are also others which can do the same, which perform distribution grid state estimation, which is called the weighted least square method. So it's a numerical method. It works in an iterative manner. And you start with the noise measurements, so that's basically what we can observe. And then you define initial state starting point x0. Right, for your state vector. And we can plug this into, so a k is equal to 0, let's say in the first iteration. You can plug this into your equations h, and you obtain a z0, right? And the difference of the observed measurements to z0 defines this difference, and we can then have this minimization problem where you get an update on delta x. So this minimization problem is basically zi minus hi, so what I write down here, divided by r. So r is a weighting factor. That's also why it's called weighted least square method, right? Which comes from the level of noise of each measurements. So I is the measurements, right? And we may have different noise levels per measurement, and R defines this noise level. So now we can update delta x in iterative manner, as mentioned, and we define a stopping criterion epsilon. This means that the state vector is being updated and updated and updated until you have the stopping criteria, and this is our final guess x. So this is called the weighted least square method. Now there are questions: how accurate is x? It typically does not work well if you have very little measurements. So it depends highly on how much measurements you have and so on. But in transmission system level, for example, it's this state-of-the-art method still, and there are lots of variations of weighted least square methods. But the open questions is always how accurate is x and how good is your convergence. And people are then including pseudo measurements, for example, here to make it then converge, which are even worse. They have very high inaccuracy or high noise levels, and so on. So now I mentioned earlier this idea of surrogate models, right? To learn a surrogate model. So for example, could we learn a surrogate model for this problem, right? So that's could be one idea. And this would mean that we apply statistical learning, where we have a set of training samples, Z and Y, which maps, again, Y is here our state, so what I called earlier X, and this is the measurement Z. So for different Zs, you will get different Ys. And then we have this inference problem where the goal becomes to learn this function f. So what we had here, let me go back. So we have here the state estimation, right? That's the goal. And basically what we are aiming at is to learn this function f through observations, through labels we have created with the weighted least square methods. So the combination here, y, comes from the numerical method I showed you beforehand. Yeah, you can apply any loss function, like the square loss for regression. You could use an ANN, any type of ANN, it doesn't matter here. To learn this function. So this is here represented in the same workflow. So what is now happening is you have the measurement Z, it goes into the function which we have trained, ANN, you get the state X, and you have obtained these labels from the numerical method I showed you earlier. So this is the loss function, right? Y minus X, the summation of it. And we can then backpropagate and basically update the ANN until we have a certain good function f. So now the challenges here are labels are not known, and if you could do anyways the weighted least square method, why would we want to have the surrogate model, right? And also the weighted least square method generates labels with errors. So that's also what I mentioned earlier. It's a local method. So there are still challenges with this. So we would learn a surrogate model which approximates basically this new numerical method. So the work which Benjamin did was to introduce weakly supervised learning, which is basically to also consider that the output is inaccurate. And that refers to a few things. So we have this noise, right, which we introduce. We have pseudo measurements, which are highly inaccurate. And then the Newton's method here would anyways give us some where we have an error. So why do we not plan also that the output is inaccurate? And we are learning with inaccurate labels, right? So the only change is here that we have y hat instead of y. And the workflow which he has developed is this, especially this weakly supervised learning workflow. We still have an ANN, or some neural network architecture, which learns this surrogate function, but we learn it in a different way. So until here, everything is the same. But what we then do is we use the same function h to evaluate basically to take the state variable inside h, right, and check how well it represents now our measurements which we have observed. So we have the difference between z and h. We have the loss function, and we backpropagate and update our artificial neural network. So basically, as you can see, these two things become now one, right? The weighted least square method and I go a bit back, and the supervised learning for state estimation. So we basically expand this here with h, and we change the loss function to the same weighted least square method. Oops, sorry. Okay, so that's the approach. Now, how do graph neural networks fit in? So as when we are applying machine learning to any engineering problem, it's important to respect the structure of the domain. As I mentioned earlier, we would like to exploit the information we have, including to induce biases and so on into the training, so we can learn more sparse models. So if we think about what we have so far used, we have used the fact that we have noise measurements in our loss function, right? Because I showed you R or sigma of the different noise levels. We have used the power flow equations, H, in our training workflow. What we have not used yet is the topology. So how the features are relating to each other, basically, right? So what neighborhoods we have. That is something which we are now going to explore. So, and then, okay, AI is already very successful in the domain of images. So I mean, I will cut this part a little bit short, but still I go through it. So there are some properties why AI is so successful in the domain of images, which is, for example, that some patterns are much smaller than the whole image. And we do not need to, that the neuron does not need to see the whole image to discover some patterns. Like here, this image contains a bird, as you can see. And to just have this information or the smaller part of the image of a beak is sufficiently to predict whether there is a beak or not, whether there is a bird or not in this image, right? The second one is that some pattern appear in different regions. So you have here two different birds, and they appear in different regions. So you have here the beak in the top left corner, and here more in the center, which means that naive approach, trivial approach would be to train basically beak detectors for every part of the image, but that's highly inefficient because the same neural network, they can basically share the parameters because they do nearly the same thing. And then I think I also don't explain how convolutions work, but the story is basically that convolutions and graph neural networks help us to translate the ideas from images to power networks, right? And that's where graph neural network comes in. So it's one example of geometric deep learning, where the grids is another geometry, and we are, like what I showed you earlier with convolutions, as we make them work for grids, we can also make them work for graphs. So, and that's also how we are using graph neural networks. So we consider a graph where the adjacency matrix is A, basically saying whether we have a connection or not in the power system or in our graph. We have the one-hot neighborhoods, Ni, which relate all the features in the neighborhood with each other. So that becomes a neighborhood feature vector X. And we introduce local functions which operate over these neighborhoods. Now, let me say a few words about the application of graph neural networks to our problem. So basically, if we think about our problem, we can think that we have a lot of those neighborhoods in one power system, right? So if this is the power system, this is the image I showed you earlier, we can learn from one neighborhood something where the same structure may also appear in the different parts of the networks. That's why we can use the graph neural network. And the graph neural network represents the topology of the power system. And the state estimation would be, so I introduced this earlier as features, right? These red and green squares. The distribution system state estimation would be basically to go from a small set of these features to the full set of features, right? Input, output. And the method which Benjamin used is called the deep statistical solver. So it basically updates edges and vertices in an iterative manner, which is also inspired by these numerical methods which I showed you earlier, the Newton method, right? And through that, you can update the edges and vertices and update the labels in iterative manner, which is then the application of the graph neural network. So let me show you some results. So we assessed 3 different case study systems. So one is the 14 bus system, so it's a smaller network. And I mentioned earlier that they have different topological configurations. So this is, for example, not meshed, but then you can see here that we have more connections inside the graph. So learning something with graph neural networks on these 2 systems may be challenging. But here you may have an advantage. But yeah, you can see these are all 3 different medium voltage systems, but they have different structure. And we assess this method on these 3 systems. So a couple of settings. We used real data, 8,640 days. We varied then the loading conditions with Gaussian noise. We assume balance system. So this is some power system technical terms, AC power flow. No, maybe not so important here, but it's also typical assumption for medium voltage systems. Then we assume measurement noise in the typical ranges, which we find from the literature, 0 to 5 to 2%, and different measurement noise for active and power measurements. Then the pseudo measurements, it's not really a Gaussian noise or so, but they follow certain distributions. So if you think about, so this is just to illustrate this maybe what generic load profile mean. So if you think about it, these are different households, right, or aggregates of households, and they may have similar aggregated correlations. So everyone leaves in the morning their house, right, and goes to work, has the same pattern of using kettle in the morning, coffee machine, and then returning in the evening. So these are all similar. But then there are also outliers and things like that inside this generic load profiles, right? So they become quite varying the smaller you go in your aggregation step. So in low voltage system, for example, you have much higher fluctuations than in an aggregated distribution system like we have here. But this is what we call pseudo measurements. So we don't know exactly, we cannot measure the loads, but we have estimations of them from previous days or from historical observations or similar neighborhoods. Then the baselines we included was one is the weighted least square method. Another one is the feed-forward neural network, and the third one is supervised DSS squared. So that's not the proposed approach, but it's a variant of it. So it uses the same architecture and the same approach to train the graph neural network, but the difference is that it has access to labels. So it's not in this kind of weakly supervised way, which I introduced you. So this is also a baseline to check whether this graph neural network actually outperforms the feed-forward neural network, for example, or not. So hyperparameter settings, bless you. We used hyperheterogeneous multi-graph neural networks, training 80% standard split, and the grid search on typical parameters. And then one other aspect we included is to assume stable systems, where you can see there are a couple of loss terms which we also included with ReLU functions, which helps the neural network basically to go to search in a certain area, because it's voltages higher or lower than 1.05 or 0.95 are very unrealistic or unstable. So we only learn for stable system. Okay, let's look into the results. So firstly, training performance on the 14-bus system. So this was this smaller system. So I go from smaller to larger. Let's start with the smaller one. So you see this two state variables, voltage levels and line loading. So this was the X earlier, right? I showed you two different X entries. So this is the first one, voltage levels, and you see the training performance on RMSE. And you see, okay, we with 600 epochs or so, I mean, it learns something, it goes down, or the RMSE reduces. Line loadings goes up first and then reduces and then stagnates a bit more. So you may have some saturation behavior already earlier. But yeah, so it's both in, this is in the order of 3% or 4%, and this is in the, goes to extremely low. And acceptable ranges are actually already here. So yeah, that's looks good for the 14-bus system, but it's also a very small system. Now let's zoom in one more step. So this is the aggregated performance, right, on all voltage levels and on all line loadings. And this is the voltage levels per each bus. So this is your node in your graph neural network. And now we show here the different baselines. So you have WLS DSS squared. So this is the proposed. Orange is the proposed. And DSS squared supervised, that's in brown. That's this the alternative method which I mentioned, which has access to labels, which means we have used the weighted least square methods, this new the numerical method to generate labels, and trained then the DSS squared model with this data. And then feed-forward neural network in blue. So what do we see here? What are these dashed lines? So the dashed lines are acceptable ranges by system operators from literature. So if you are here at 0.005, this is really good state estimation, right? And this is not acceptable, and this would be acceptable. Yeah, but not that great. These are just like quantitative values which are used in the literature to say state estimation is acceptable or not. You can see that all of the approaches are actually also WLS gives very low RMSE. Also we would not conclude from here that there is any major difference in the other methods. But yeah, you can see, okay, the DSS squared, FFN, and DSS squared learn something. Now, if you look into the second state variable, which is the line loadings, we see there are some differences. So firstly, the gray method is not so great for some of the lines. But also you see that the orange, so this is the proposed method, is not has quite high errors on, and this is in the order of 20 to 30%, so this is quite high in 2 lines, 12 and 13. And this one was because they were modeled incorrectly, or you can also see that inaccurate model has an influence on the output, on the accuracy of this of the proposed method. Right, so you can also think from a different perspective. If you make wrong assumptions in the physics, the model inaccuracies, basically, you may have the same downside as any other numerical method, right? Which means that the error increases here in this area. Now let's move into the summary of the results. So you have, we show accuracy here first on these 3 metrics I introduced you, but now we split trafos and line loadings. So we have two RMSE. One is basically for these guys, and the other one is for these ones. So that's the difference between these 2 lines. And the 14 bus system is this is just the summary of the previous results, right? WLS performs well on line loadings, is the best method, and then the supervised DSS squared has lower errors on the voltage levels. So now let's go into the other 2 systems on the same 3 metrics, so 70 and 179 bus systems. So here you see now in green we have the proposed method outperforming, but you also see that we have included other baselines because WLS star is not exactly the same as WLS. The difference is that for this, so the motivation of this work was that sometimes we cannot converge with WLS method, right? And this is now what we experience in the 70 bus system. Because some of these, if you just apply standard WLS, it may not converge. And we made WLS then converge with increased convergence rate or with higher tolerance and more iterations in the 179 bus system. And maybe I jump to the convergence results. So you can see that 25% converged of the 8,640 days in the 70 bus system only. And here, if we use also modified WLS, we have 53% because none would have been converged with the standard WLS. So it shows you this benefit that if we have trained WSS squared, we get reasonable estimates of the state, and we can ensure convergence to 100%, right? Because neural network always gives you output. Now, computational time. So we have here basically a reduction of computational time in the order of, this is WLS scaling behavior from 70 to 170 bus systems. So this is tripling the number of buses. So remember the plot I showed you earlier with the power system analysis, how it scales with the number of buses. That's basically here just the numbers. So here we triple the number of nodes, and the computational time for WLS is times 10, right? Whereas for the DSS squared, we have just a duplication. So the scaling behavior is better in terms of real time when you just are interested to produce the label. So now behavior to noise and other results. So an interesting finding was that DSS squared successfully canceled noise because noise has only influence on the neighborhood. And if we are even including missing data or we use erroneous data, we have also very limited impact. So this is the DSS squared versus WLS in both of the figures, right? And you see that high noise levels here impact quite drastically WLS and does not impact much the DSS squared. So this shows us we actually learned a denoiser for through this approach. Yeah, the reason why this performs better is that the local that some missing values only influence in the neighborhood, but the WLS has yeah, there one missing value can have a drastic influence on the on all state variables basically. So now we export also this generalization capability to different loading levels and generation levels. So these are not, they were not part of the training. So this is really out of distribution, right? So you have training domain, which of course has also variations on loading levels. And we go away from training domain and we have much higher variations of loading levels or lower ones. And this is what you see here. And you can see that there is some limit on DSS squared. So at a certain amount of changing, plus 25% on loading levels, and on generation 100% or the other way around. So yeah, you see there is a very large increase of error. And this is then the limitation. So let me conclude this talk. So now the last part was an example of how we use graph neural networks for distribution system state estimation. But of course, there are other problems in power systems where we can make use of them. And I think that there's a few drivers at the moment is to combine basically statistics, machine learning, and mathematical optimization. So it requires a varying skill set to really advance on the power system problems at the moment. That's one message I want to send. And the second is that through this understanding or through this interdisciplinary work which we are doing, we can find new methods which basically like learn without any labels, use structural information like these three points which I showed you, the noise, physical equations, and topological information, right? This is an example. So to basically learn sparse models for power systems in order to address these issues here, like the cost of dimensionality, poor performance on out of distributions data, and possibly then, yeah, maybe guarantees or something like that in the future, who knows. Yeah, there are also some challenges, of course, with what makes this type of research not so easy, especially when it comes to GNNs to power systems. So one is that we have not always very well connected meshed systems or graphs. We are still working on where we really want to enforce physical equations, not regularizing with them. Then we, yeah, sometimes we have these Newton-Raphson methods, for example, give you multiple solutions, not only one. So that's also not necessarily how graph neural network may work. And then we have also changing graphs and different problems which are not just a match to what graph neural networks were designed and for. So yeah, I think that's all. And if you are interested to either ask now or follow up in some email.